All right, hey guys. So this is part 2 of the video on optimization. I'm still hoping to give the quiz Wednesday as long as everything kind of plays out right. And in the first video, I think we did numbers 1, 2, 3, and then something from the homework too. And honestly, I don't think I want to do 4. 4 is not bad, and I'll talk about it maybe a little bit, but it's a little tough. Like setting up the equation isn't bad, and then solving it's a little nasty, so maybe I don't want to do that. But yeah, let's talk about it for a minute. Give me a second, messing around with some plugs here. Okay, so yeah, this one about the two towers that are 30 feet apart. One is 12 feet high, the other is 28 feet high. So you can see I've drawn some towers out. This is the shorter one, that's one's 12, then the taller one is 28. And we know the distance between them is 30. So if we were going to mark this distance on the smaller tower, if we call that x, then the other one would be 30 minus x. And that's us essentially treating this 30 feet apart like it's our constraint equation. Like, you don't always have to be so formal about the constraint equation, but technically if these two distances were x and y, then our constraint equation would be that x plus y equals 30. But I hope that's so obvious that we would just subtract x from both sides. And then instead of ever writing y, you would just immediately kind of write that if one dimension is x, the other one's 30 minus x. And that's totally fine. So now what that means is if we're looking to minimize the amount of wire we use, well then the wires are the hypotenuse of these two right triangles, right? These are assuming the towers are forming 90 degrees with the ground. Then the length of wire 1 would be the square root of 12 squared plus x squared, and wire 2 would be the square root of 28 squared plus 30 minus x squared. So this would be the equation we want to optimize, that just that w, the total amount of wire used, is wire 1 plus wire 2. So if we were to actually set this thing up, then w would be the square root of 12 squared plus x squared plus the square root of 28 squared plus 30 minus x squared. So, the worksheet I gave you guys really would have us stop here. Like writing the equation was kind of the end goal, was just to get to the equation. But I wanted to actually solve. And solving this one's pretty ugly, so I would say it's fine. Like if you understood how to set this up, that's great. And from here we could just move on. So I'm going to do that. So onto the homework. Number 1 is kind of similar to number 1 from the practice problems that we did on the worksheet. So let's try this one. Hopefully you've already tried it yourself. I really do hope that you're doing these problems on your own before you're watching these videos. So if you did, it says what's the smallest product of two numbers? So, okay, that's my optimization equation right away. So my optimization equation, which I want to minimize, is literally just the equation x times y equals some product. And I want to keep p to a minimum. So again, the big problem we have is we've got p defined in terms of x and y. That's not great. So we need a constraint equation. And as far as constraint equation goes, this one's pretty simple. It says given that one number is 7 greater than the other. So we could basically just say, okay, so I guess x is going to be the one that's 7 units greater than y. Okay, so it's literally already solved. We probably just never should have even written x times y equals p. If it was obvious to you that the equation would just be some number times some number that's bigger by 7, then you could go ahead and just start right there. That would be fine. But technically, the way I've written my stuff out, actually the x is going to become a y plus 7. So we actually should be looking at y plus 7 times y. Now, same difference. Depending on how we define our variables, you might actually disagree with your friend. Let's just pretend for a second that the answer was 3 and 10. You might find that x is 3 and y is 10, and your buddy might find that y is 3 and x is 10, and you're not wrong, because we're not really assigning these numbers to specific variables. You're just solving for the numbers. And if you say that the answer is 3 and 10 and someone else says the answer is 10 and 3, it doesn't matter. Okay, so that's not a big deal. Anyway, now that we're all set up, I would certainly distribute the y before I differentiated. So we now have p equals y squared plus 7y. Then I want to differentiate to get my derivative. So p prime is now 2y plus 7. And we know that my product should take on an extreme value only when the derivative is 0. So we'll set this to 0 and solve. So 2y equals negative 7. So y equals, you know I love fractions, so it should be 7 over 2 for me. But that is just negative 3.5. And if you want to use that decimal, you can, because it is exact. But that's the value of y, which means the value of x must just be what you get when you add 7 to this. So if you add 7 to that, then you would get an x that equals negative 3.5 plus 7, which would be what? 3.5 again, right? But positive 3.5? Yeah. So that's it. What is the smallest product? Oh, okay. So that's kind of good. For this problem, they didn't actually ask us for the two numbers. They asked us for the product. So make sure you give me the final answer that says, the actual product is x times y, which means it's going to be negative 7 halves times positive 7 halves. So that's going to be negative 49 fourths. And that's actually your final answer, because you want to give that minimized product. And oh, by the way, I did kind of forget. How do we know this is a minimum and not a maximum? Maybe that's the maximum value, right? So technically we're supposed to test these values. So we move that out of the way. And just to remind you, we can pretty easily test whether we're getting a max or a min at negative 3.5 by just building a sign chart. The dog again. Okay, the dog has been quieted. What were we doing? We were doing a semi-unnecessary step where we're testing the critical value that we found to make sure it's actually a minimum. So negative 7 halves is our y. So if we test the derivative, this is the derivative right here. It's just a linear function. So surely to the left of that, we would come out to be negative, and to the right of this, we would come out to be positive. And so based on those results, we know that we can say, therefore, did you guys know this 3 dots thing means therefore? Oh, my face is in the way. I'm going to turn my face off. There, no face. Anyway, these 3 dots mean therefore. So based on this, we can say, therefore, P has a min when y equals negative 7 halves, because P prime changes signs. From negative to positive. Yeah, so there you go. All right, and then technically I should have done that before calculating anything else, but whatever. We know that y is negative 3.5, then x is positive 3.5, so our minimized product is negative 49 fourths. That's it. That should be hopefully one that doesn't feel too bad. Let's try number 2. 2 says, if the product of two positive numbers is 36 and the sum of the first number plus 4 times the second number is a minimum, then what are the two numbers? So I see the word minimum, and it says I'm minimizing the sum, so that would be my optimization equation. And it just says 2 numbers, so those 2 numbers, we'll probably just use x and y, that's pretty standard. So the sum of the first number, I guess that'll be x, plus 4 times the second number, so x plus 4y, and that equals some sum, and we want this minimized. So again, too many variables, so we know that we need a constraint equation. And the constraint equation is the fact that the product of these numbers is 36. So x times y equals 36. Although technically, you could have two negatives multiplying to give a positive, so it does say two positives, so technically you should be stating also that x has to be positive and y has to be positive. So it's almost like really we have three constraint equations. I think if you left these out, I wouldn't necessarily care, but obviously it would be bad if you told me the answer was -4 and -9 because they're supposed to be positive. All right, anyway, the fact that x times y equals 36, of course, tells us that either x is equal to 36 divided by y or y is equal to 36 divided by x. And if you like working in terms of x, then that means you want to solve for y. So you get 36 over x, because now we can substitute that in. So leave x alone, but replace y with an expression that has x in it. So we'll take this expression right here, plug it in. And again, we have a pretty simple equation here that hopefully we should be able to work with just fine. But again, before I differentiate, I'll clean this up just a smidge. This will be an x plus whatever 4 times 36 is, which I think is 144. Oopsies. So technically it's 144 over x. But again, to make using power rule a little bit easier, let's take the x, bring it up, and just give it an exponent of -1. So that is still s. And we should differentiate now to figure out what s prime is. And the derivative of x just gives us 1. Then this derivative will be minus 144 times x to the -2. And we'll set that equal to 0 and we'll solve. So we get a 1 that equals 144 over x squared. Is that how I want to do this? That's not the best way to do this. I changed my mind. Just to be a little more thorough, technically this should be 144 over x squared, which means if I let this 1 become an x squared over x squared, then I can combine these because I now have a common denominator. And that's really the way you're supposed to solve equations so that you don't miss any solutions, even though often the solutions that you miss by doing this end up being extraneous anyway. But still, I don't want to reinforce any bad habits. So if I combine this now, I get x squared minus 144 in my numerator, and downstairs in the denominator I get x squared. And so technically this equation has 3 solutions, because if I take the numerator, set it equal to 0, then that's going to give plus or minus 12. So we get a -12 and a +12. But if we're just looking for critical values, then the zeros of the denominator should still be of interest to us. And so that's giving us 0 as well. But again, like I said, if we kind of do this extra work to try to solve this equation appropriately by turning it into a rational equation and considering the numerator and the denominator, well, look what we get. We get a -12 that violates this rule about how we have to be positive. So this is extraneous. Then we also get 0, which technically isn't positive either. You have to be strictly greater than 0. So that's actually not an option for us either. So really the only number that's even in contention to maximize or minimize our sum is the 12. I forgot to turn my face back on. God forbid. Okay, I'm back. So I do want to keep reinforcing these good habits, so let's test to make sure that positive 12 is actually a place where a minimum happens and not a maximum. So I'll draw a number line. Now if you just drew 12, you might screw this up, because we can see from the fact that we have 3 zeros that our derivative is going to change signs 4 times. So you might want to include those values too. Although really the only thing you would need to test is the 2 regions defined by the 12. So just the region between 0 and 12. and the region between 12 and infinity. Just test those. But the reason I mention this is because if you tried to test the region between 0 and 12 by plugging in like negative 100, then you'd really be testing this region. We don't care about that region. We just care about this one. So we're going to go ahead and test our derivative, which is this guy here. Not its best look. Maybe we could test this version. And again, we could test it knowing that this numerator was an x plus 12 and an x minus 12. And that's all getting divided by x squared, which is really an x times an x. This green version here might be the easiest to test using the rules in the way that we test, where all we care about is positive, negative. So if I plug in 6, then obviously in the numerator I get a positive times a negative. And at 6 I'm getting a positive times a positive. So I see an odd number of negatives, which means I'm negative. Then if I pick a number bigger than 12, like 100 or something, then everybody's positive. Positive, 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 so we're positive. And again, all this was just to prove that the extreme value we got at 12 is really a minimum. We kind of knew it had to be. The whole point was we were trying to minimize what was going on. If this wasn't a minimum, would have been kind of in a big trouble. So where are we? I guess I just decided that x is 12 for sure. So the next step would be figure out what y is, and we've got a handy dandy equation right over here. So we know that y is equal to 36 divided by 12, which is, that's 3, right? Oh, okay, I was getting confused for a second. I was thinking about the other problem where we were supposed to be bigger by 7, and 3 plus 7 isn't 12, but that's okay because that's not the one that matters. So here's the two numbers. Now is that the answer to the question, or is the answer to the question the sum? Let's read it. It says, what are the two numbers? So we're done. We could say here that the two numbers that minimize our sum are 12 and 3. But I think we're fine. I don't know if we need to write a sentence. I'll just stop here. Just in case, again, if you were asked to actually find what the minimum sum was, you just plug into the sum equation, of course, and you would be getting 12 plus 4 times 3, which, surprise, surprise, is 12. There seems to be something going on here that when the two numbers are the same, that tends to give us our minimum or maximum. But our minimal possible sum is 24. All right, that's number 2. So 3 apparently is the one I did in the other video. So if you want to hear more about 3, just tune into the other video. And here's 4. 4, oh, this is another one of the tower problems, so I'm going to go ahead and skip this one again. You know, if you skipped the start of this video, I sort of talked about how to handle these two towers problems. But I'm not going to ask about these, I decided. But if you're really curious, we said these two tower problems are just two right triangles. And there's a wire going from here to here, so call that W1. This hypotenuse is a second wire, W2. And these problems revolve around trying to minimize the amount of wire that you use. So you want to minimize W1 plus W2. And W1 would come from the Pythagorean theorem. It would be the square root of this height and whatever this base length is. So you end up with like an h squared plus whatever the base is squared. So stuff. Then you add to that the second wire, which will be the other height. So you'll do height squared plus whatever the base is squared. And then just the math to actually solve this was a little bit annoying, so I don't want to do these two. That's fine. We don't need to. So here's 5. 5 says, which point on the graph of y equals 4 minus x squared are closest to the point 0, 2? It says which points on the graph are closest. So let's get a look at what that means in a sec. Okay, so I made you this Desmos thing so you can sort of picture what's going on. But this red graph is the graph of 4 minus x squared. That's our equation. And we want to find the points that are closest to the point 0, 2. That's this blue dot right here. I can zoom in on this a little bit, maybe, if that's worth it. But I also put like a little circle around this point. and I can make that circle get bigger and smaller. And so the idea is, well, the point that's closest would be the very first point that I hit as I expand this circle. So as I expand this out and out and out and out, you can see that it's going to hit the parabola in two places at the same time. So there it is, right there. So it looks like when my radius is about 1.32, I'm hitting a point on the right side of the parabola, I'm hitting a point on the left side of the parabola, and those 2 points, therefore, must be the 2 points that are the closest to this point in the middle. If I open this up wider, we could see we get 4 points of intersection, but they're not the closest to this point. If I opened up even further, if I pass through the vertex up top, then we get 3 points of intersection, which is just kind of interesting. I just want you guys to think about how the ways that a circle could intersect with a parabola. And obviously if I opened even wider, then we still get 2 points of intersection down here on the parabola, but they're not at a minimum distance. They're actually quite far away. But I don't know. I think this is helpful to help you wrap your heads around it, but obviously my circle could not hit the parabola at all. Then the moment that minimizes our distance is the moment when we are, this is called being internally, well actually it's external. So the parabola is externally tangent to the circle, right? It just barely touches. Then if I opened up wider, then the parabola is acting kind of like a secant line. It's hitting in two places and two places for a total of 4. If you open your parabola just right, meaning with a radius of 2, you can get 3 points of intersection. Any wider than that, you're only getting 2 points. Just something I found interesting. Anyway, I'm going to turn this off because we're not allowed to do this by graphing anyway. We've got to do it by hand. So, is this the one I turn off? Turn off. All right, so how do I actually do this by hand? To do it by hand, I'll move my keyboard. And we'll write our equations. And of course, we've done a problem kind of like this before, so we know that our constraint equation is just the equation of the given graph, the parabola. So our constraint equation is the y equals 4 minus x squared. And the optimization equation that we're trying to minimize because we're trying to be as close as possible. That comes from the distance formula. So hopefully you remember the distance formula was the big old square root of x1 minus x2, or the reverse, x2 minus x1, doesn't matter, plus y1 minus y2. I don't know why I'm writing it like that either. I like x2 minus x1 much more. Anyway, so who are we talking about when we talk about x1, x2, and blah, blah, blah? Well, go back to the picture I just showed you where we had this red parabola that was opening down. We had some blue point on the y-axis. Well, we're trying to minimize that distance from blue point to parabola, and we saw it was some point roughly there. So that point that we're trying to find, that would be plain old xy. This point would be our variables. And of course the given point was 0, 2, so I know those coordinates. But these are the values I would plug into my distance formula. So the distance formula would be d equals the square root of, and then it would be x minus 0 squared plus y minus 2 squared. And this would be the equation we're trying to minimize this equation. So that means we want to find the zeros of its derivative. But again, too many variables, but I've got a handy dandy expression over here. If y is equal to 4 minus x squared, then I can plug that in and do a little cleaning up at the same time. So x minus 0 squared is obviously just x squared. Then instead of y, I can substitute in the 4 minus x squared expression. And then we're still subtracting 2 from that. And we're still squaring that whole entire result. And so here we are. This now is the equation that we want to optimize. So I'd want to simplify this a little further and take its derivative. So if we're simplifying, then first thing we would do is, I guess, just combine the 4 and the minus 2. So you'd have an x squared plus 2 minus x squared. And then we're squaring that. So if we're squaring 2 minus x squared, we've got to FOIL that out. And that's going to give us d equals the square root of, we've got the x squared. Then if we square this, we're going to have a 2 times 2 giving 4. Then the outer terms and the inner terms will both be minus 2x squared. So that'll be minus 4x squared in the middle. And our last term will be plus x to the 4th. And then I do have like terms in this x squared and this minus 4x squared. So when all is said and done, my equation is going to be a big old radical that has an x to the 4th underneath minus 3x squareds and then plus 1x plus 4, sorry. Okay, but that's it. So we now need to differentiate this guy, which means, and by the way, we would rewrite this as just to the power of 1/2, right? And ignore the radical because we want to use that power rule. So that means d prime is going to be 1/2 of this entire expression, now raised to the power of negative 1/2. So bring down the x to the 4th minus 3x squared plus 4. And then don't forget chain rule. We're going to get a second factor. That's a 4x cubed minus 6x, and then technically plus 0. But that's your whole derivative. And so to find the zeros of that, let's clean it up a bit. All right, so again, anything to this negative power, we're going to push down into the denominator. And from the 1/2, we know the 2 is down in the denominator also. And I guess I'll turn the 1/2 back into a radical. So downstairs we've got 2 times the square root of the x to the 4th minus 3x squared plus 4. And up in the numerator we've got the 4x cubed minus 6x. So this is our derivative, kind of in its simplified form. We want this to equal 0. So we'll set it equal to 0 and we'll try to solve. And of course our solutions come from when the numerator is 0. So again, we're basically just ignoring the denominator and saying 4x cubed minus 6x, setting that equal to 0. I see I can factor out an x, so I do, and I get 4x squared minus 6 equals 0. And that tells me that, well, now that I'm factored more, I can split this, and I see that the x will be 0 when x is 0. So x equals 0 is now officially a critical value. Now the other one, the 4x squared minus 6, if we let that equal 0, then we'd add 6 to both sides and divide by 4. So we're looking at an x squared that equals 6 over 4, which reduces down to 3 over 2. Then we take the square root, remembering that that gives us 2 answers. It gives us plus or minus square root 3 over 2, which, by the way, is square root of 3 over square root of 2. And then we can clean up our denominator by multiplying by root 2 over root 2. So the final answers here would be plus or minus the square root of 6 divided by normal 2. So far we have 3 critical values already, and that's before we even consider the denominator, which also produces critical values when it equals 0. So if we had 2 times the square root of x